All right, we're ambitiously going to try to get through 32 slides in 20 minutes, so we'll see how we do. So yeah, I'm Pat Fedick. I'm over at the Naval Air Warfare Center Weapons Division. I'll talk about some Navy applications of field portable mass specs, coupled with our 3D printed cone ion source. So Navy's need for portable instrumentation, right? You know, chemical threats, environmental contamination, those probably are the two major ones. Our group also works on online reaction monitoring for when we're producing energetics, and then some real-time environmental remediation. So I'm going to really focus on those top two for this particular talk. But when you're thinking about bringing a field portable, out to the field and having the warfighter potentially use this, you're thinking about maybe an 18-year-old who maybe had high school chemistry, if you're lucky. So probably not a Ph.D. scientist like half the people in this room that have been running mass specs for the last forever. So when we were looking for a field portable mass spec, we were also thinking, hey, how do we do the front end to couple to this field portable mass spec so that my 18-year-old, newly enlisted person could go in and actually use this? So probably about maybe 6 years ago, we started working on this technique called 3D printed cone spray ionization. So a lot of people are familiar with paper spray. You have your one-dimensional, you could swab a surface. Then the invention of paper cone spray and filter cone spray came out, where you could go and kind of origami this cone and put your solid sample into the cone and spray. The problem with it was that you had to kind of do that origami, so the reproducibility, how are we going to have, again, our 18-year-old in the field trying to make a three-dimensional cone? So we came up with this idea where we can 3D print with conductive plastics, and the whole main basis of 3D printed cone spray is we can just put bulk solid. So you go in, let's say you're looking for chemical warfare agents, or explosives, or drugs, whatever it is, you literally load your solid into the cone, you add your solvent, you add your high voltage, and you actually form a Taylor cone right at the tip of the ion source. All of your bulk matrix is trapped within the cone. There's about a 10 micron hole at the tip of the cone for everything to pass through. So I'm going to show you guys a number of applications that we've done over the years. This one was just published this past year for trace and bulk detection of post-burn and post-blast energetics. So this was work that was done in collaboration with Chris Mulligan's group at Illinois State University and the ATF. So our collaborator at ATF constantly has to go out to the field and collect samples, whether it's post-burn propellants. So again, that was them doing it in the lab, burning a propellant that had nitroglycerin and ethyl centralite, one of the stabilizers in there. We can go and scoop up those remnants that you see down, maybe, right down there, throw that directly into the cone, add your solvent, spray, and right away we can see, okay, we have ECNG. Some homemade post explosives, so TATP, super easy to make in your house, very unstable, so again, but highly used by nefarious individuals. So we had TATP loaded up into this straw, detonated it, picked up the straw fragments, threw it into the cone, add your solvent, sprayed right into the MT30. So again, you could see we can fragment it, detect it, no problem. And it was just kind of serendipitous that our ATF colleague was out at our lab when we were doing one of our thermal destruction events, where we get rid of some of our energetic waste. So this was a pile of about 2,000 pounds of flake TNT and a bunch of new energetics. I can say for this mass spectra being so clean and full scan on an MT30, you could probably taste the TNT in the air by the time that we went to go and sample, so a little bit biased on that one. But all of these things for energetics, whether it's from the forensic standpoint, or if you're also looking for example, there are certain explosives that are only being produced by the military, for example, based on the complexity. So if you come to a crater or something happened and you see that it's TATP, well, maybe it's homegrown terrorist, something like that. But if you have something along the lines of CL20, it's going to be a state actor. So real quick way of going and sampling solids, putting it in, and what we've really tried to develop between the cone spray and then the field portable mass spec is can I train my scientist to scoop something into a cone or place something into a cone, apply high voltage in solvent, and get your mass spectra. So this will be my talk on Tuesday afternoon. So I just have the parts on the MT30. We actually started this project so long ago that we were originally doing it on the MT50. But what we were looking at was adapting 3D printed cone spray to a bunch of different commercial portable field portables. So again, our collaborator Chris Mulligan at Illinois State, and now we were working with Army Aberdeen Proving Ground, or DevCom CBC now. So they have a base spec, we have the MassTechs, and then ISU has the FLIR system. So I'm kind of condensing a lot of this just to focus on what we did with the MT30. But again, thinking about the warfighter, thinking about how are we going to go and sample. So we had two groups. We had first-year undergrad students that had really never worked with the cones before, and then we had folks from my group who had been developing cones for the last couple of years. All of the live agent work was actually done on the base spec, but this is a simulant for some of our V agents. So we doped it into topsoil, sand, and gravel, and we made the individuals that were taking the analyst wear chemical warfare agent gloves. So you have your nitrile gloves on, and then you have the big rubber things. We didn't actually make them don the full suit just because everyone said I'd be a little bit mean if I made them do that in the desert. But what we were looking at, we had about 600 blinded samples that we gave split between the two groups. So this is just kind of the overall table. I'll really show you the next slide where some of the regression goes. But what we had them do was as soon as they scooped the soil, we timed them. So how long did it take you wearing the gloves, position it in front of the cone in front of the mass spec, the field portable, and go and start collecting spectra. So how does this work in the real world? And then also trying to see how this would relate to, like, again, when you're in theater, how long will it actually take you to go and sample all of this? And do we have the reliability that we're not really getting any false positives or false negatives? So it turns out we did get one false positive, unfortunately, when we were looking at the, so 1 out of 600 ain't terrible. When we were looking at the blank beforehand, we really should have had cleaned the capillary. But the more important thing, especially when you're talking about chemical warfare agents, we had no false negatives, which is, again, more concerning. So false positive, all the alarm bells goes off. You go and make sure everyone's done in their PPE. Oh, it's a false alarm, all good. You have false negatives, you really have problems. So one of the things that we were, again, like I said, kind of tracking over time. So this is one individual, this is a second individual. As they continue to collect all of these blinded samples, their sampling time started to decrease. I don't think this was like statistically significant, but you could kind of see the downward trend. And then also even just some of the variability starts to stop clustering or starts to cluster a little bit more. So this was a good sign when we're going to go and try to train, again, our warfighters on how to use this. We go run through 100 samples. They're pretty proficient at it. And again, pretty rapid results. You can see down here in front of the MT30. So we then woke up the one day with the great idea of, hey, let's just spray chemical warfare agents on everything that we could find in the lab. So I kind of looked a little homeless when I left because that's my jeans, that's my shirt, that was part of my boot, my wallet, newspaper. My wife was very angry at me because we live in the middle of the Mojave Desert. So this was one of our few roses that actually are alive out there. Same thing, not much grass out there, but we got some of that, a chicken feather, and then because we were doing all this work, I figured I deserved a beer, so got to drink one of those in the lab. But the main thing about the cones and the portables is if it fits into the cone and you could apply solvent and a high voltage, you could extract that, again, this is the TEPP, the simulant for the warfare agent, right off of chicken feathers. So moving forward, now I guess we're kind of going backwards in chronological order. We developed this on the MTE50 originally, and we were, again, thinking about the warfighter in mind. How do we get this so that I'm not sitting there with a copper clip and trying to position, my Taylor cone in front of everything? So again, us in the Mulligan group, we developed this auto sampler. Now, this first edition that I'm showing here, that this one was published, was absolutely grad school ghetto chic. You know, we had all commercial parts from, I think this was all mainly Thor Labs, 3D printed top. You could throw in the cones into each one, but if you can have really good eyes, there's just your high voltage wire dangling there. So as the mass or as the autosampler would position it in front of the mass inlet, it would contact with the high voltage source, and it worked. Now this was sitting on a ring stand, nothing was bolted onto the front of the MTE, but we could go and do 8 samples completely automated. It would add the solvent for you, it would rotate, it would collect the spectrum for 30 seconds, and keep going through. So we've applied this to PFAS in soil. So this was, I think, in sand, so PFOS and PFOA, your C8s that are pretty prominent. Hydrocodone and tramadol. So luckily I broke my foot in a motorcycle accident and I had leftover pills, and we're like, yes, let's throw it on MT30 and see what goes. And then the dog was sick, so we had 2 controlled substances. Again, you just throw the bulk pill in and we could go and extract it off and shoot it right into the MTE. Again, chemical warfare agents, so this was just my lab coat cut up again, and now we had 2 different simulants, and you could even do synthetic cannabinoids in smoking tobacco. So once we got the MTE30, we were saying, all right, we need to make some improvements. Again, we want to make this so that law enforcement or the warfighter could really use this really easily. So again, originally it was just this 3D printed top. Now we have ridges. You'll see in a minute there's a ball bearing. The high voltage is, so it's dual extruded, so all the black portions are all conductive as well. So we can now apply the voltage and never ever touch the cone, which is pretty nice. We also built this stand, so this bolts right onto the front end of the MTE30 to keep everything aligned. Again, we now apply the high voltage through a ball bearing that sits on that track, and this was just a piece that held the ball bearing on the auto sampler. So you can kind of see how that works now. It adds the solvent, it aligns, the high voltage is being applied, moves on to the next sample. And we've now started taking this out to the fields. So again, you know, a lot of the stuff, if you ever, going back in the day when I was working on field portables, you'd always work on a field portable, but it was in the lab, and you'd say, oh yes, one day we could take this out to the field and go and sample, and all of those papers in, like, you know, the 2010s-ish for the most part were all like, oh yeah, look, we did it on a field portable. Great, but you're in a lab condition, you know what I mean? Like, how are you really doing this? So again, now you can kind of see the auto sampler out there. We run the syringe pump and that off of little Milwaukee battery packs. And then obviously the MT30s on batteries as well. So switching from chemical threats, but now towards environmental. At this legacy AFFF firefighting range. So again, the aqueous foam forming foams, that's what has your PFAS in it that everyone's concerned about. So at this particular test site is where they validate now all the fluorine-free foams. So everything that's being used from now on. But when they have to validate the fluorine-free foams, they have to spray AFFF for that validation. So what we wanted to do was look at some of the soil around this particular site. So a bunch of different PFAS standards that we loaded up into the library. And we had this, it's about a quarter mile going lengthwise, a quarter mile this way, where we wanted to go and screen. So right in D and E is where the mini deck is. And then C, B, and A, again, they've been using this pit for about 70 years-ish for fire training. This used to be where some of the runoff went. Now it's all collected in these things in slide F, these big towers, to keep all the waste. But back in the day, before we realized that PFAS was probably bad, that whole pit back there had quite a bit of PFAS-laden material. So again, here's some spectra based off of the MT30 where we were taken. So here's just one sample from A, and again, you could see the different PFAS that we could detect. This was all full scan data. And that really, then we went and confirmed it with MSMS. So again, PFAS has these nice losses of 50 usually as you go and start cleaving each CF2 going down. So again, this all really tracked with what we would do on a benchtop. And really what we've been using the MTE30 now is for that pre-screen. So we made sure that we could detect PFAS in each one of these particular corridors. And then we did our traditional take a sample, bring it back to the lab, break this out a lot more on a LTQ or an Orbi, where, again, we probably get lower limits of detection and maybe a little bit more specificity. But the MTE30 went and said, hey, yeah, you don't need to go and screen over there because we're not detecting any PFAS. Why waste your sampling and all the, again, if you're going to do an extraction or sample prep, we know that this area is, needs to be mapped in more detail. So this was the one slide on LTQ data, but you could even see, hey, back where that pit was, way higher intensities of, PFOA. As you go back to over here where there should be really no agent released, we see practically nothing, intensity of 2. So is that even real? I don't know. So the last thing that I'll talk about, so I think I actually am nailing this in under 20 minutes, is our group is also interested in degrading PFAS. So we have a method using boron nitride nanomaterials and as a photocatalyst, and it just cleaves the CF2 unit as it keeps going along. So we use these boron nitride nanomaterials, different nanopowders, nanobarbs, nanotubes, put it in the light and the reactor. And Eleanor will be giving a talk on this on Tuesday morning. But where we're moving from taking, she was taking aliquots every 30 minutes and running it. Now we're moving towards a flow system where, again, we'll be continuously monitoring. So this was over however long that, and you could detect the PFOA and the C8 and then the C7 as well in here. So again, starting to move this to inline mass spec. This spectra was just collected like a week ago before we left. So this is kind of the new stuff that we're doing in the lab. So again, kind of like what Enrico was saying, you can bring this right to your reactor. And the reason why we're doing this inline mass spectrometry is as we're developing this remediation technique, you're going to want to put that into the field. So you can now keep going back to your reactor, that's in the field and take an aliquot, or just put your field portable mass spec next to it, tee it up, and then have real-time monitoring or trigger it whenever you want to take a sample. And now you don't have to keep bringing it back. And we can see, okay, wait, maybe the photocatalyst needs to be regenerated because we're not getting the same degradation rates or things like that. With that, thank you, MassTech, for inviting me back out here. Thank you for being an awesome collaborator for the last 5 years. I've done pretty much none of the work, so it's all been done by all the interns and postdocs in my group. Again, the Mulligan group, ATF with Ryan Bain and Aberdeen Proving Ground. And the last shameless plug, so if you're looking for MT30 talks, Eleanor, like I said, we'll talk a little bit at the end on adapting that for inline. I have a talk Tuesday afternoon on chemical warfare agents, so get a little bit more detail. And then Jamie has a poster on Thursday that really goes into all of the field portable mass spec, mapping out that field. And with that, I'd be happy to take any questions.
I do have a question, but I'll let Peter ask first. How does it work in high humidity? Does it come with an umbrella?
So, do you know what, I should have mentioned that when we were doing the field portable work out for the PFAS range, I was a little bit of a jerk, so I sent the postdocs out there when it was 120 degrees. So the MT30 does not like 120 degrees in direct sunlight. But I think when you guys went back out, it was like 90 degrees.
85 and we did it
Under a tent, and then it was fine. But humidity-wise, we have none in the desert. So we haven't really tested it in high humidity places. For that PFAS grant, we have 2 more locations next year, and we're trying to get somewhere to the coast. One, because I'd rather be at the beach than than anywhere. So we'll get back to you, maybe next year.
I have a question in regards to the sampling station. Do you deliver like the solvent? Do you have like a little pump that delivers?
Yes, we have
aliquots of the solvent, or is it just continuous flow?
So it's on a program where it will dispense pretty much a milliliter and then wait for however long you have a program before it rotates over.
That's pretty awesome. That's pretty cool.
So yeah, the idea is that, and especially now we're working with you guys on the database. So can we get it so that everything, it looks at MS, or looks at MS, sees a threat, MSMSs it, because then all we literally need to have our warfighter do is scoop, split, and hit go.
Yeah, exactly.